although the parallel axis theorem is useful in integration, where it's most often used is when we can represent an object as a superposition of composite shapes, and then we can look up the values of mass moments for objects around various axes through their centers of mass, and use these expressions to find mass moments about some arbitrary axis using the parallel axis theorem. So we have two examples to look at. The first one involves this pendulum, which consists of a slender rod AB with linear mass density 8 times 10 to the minus 4th kilogram per millimeter. And at the end of the pendulum, we have a square plate with a circular hole that has an areal mass density of 3 times 10 to the minus 5th kilogram per millimeter squared. What we want to do first is determine the location of the mass center G. Again, often we write our rotational dynamics equations by taking moments about G. So we want the location of the mass center G, then we want the moment of inertia about an axis parallel to Z that passes through G, and then separately we want to determine the radius of gyration about point A. So we have an XYZ coordinate system established in this problem. We need to find the center of mass first, and let's just first begin by sketching approximately where the centers of mass are of the individual constituents. So we know the center of mass of the rod is going to be half its length. It's going to be 70 millimeters from the origin. Y will be minus 70 millimeters in this case. And then both the square plate and the hole are going to have centers right here, which are 140 plus 30, or 170 millimeters from the origin. We'll call the slender rod 1. We'll call the square plate 2, and we'll call the hole 3. For the slender rod, we have the following mass. We have a linear density of 8 times 10 to the minus 4th kilogram per millimeter, and we're multiplying that by 140 millimeters, and that's giving us a mass of 0.112 kilograms. The Y center of the slender rod is half its length. It's in the minus Y direction, so it's going to be minus 70 millimeters. For the square plate, its mass is its areal density 3 times 10 to the minus 5th kilograms per millimeter squared, and it's 60 millimeters on a side. And that number turns out to be 0.108 kilograms. Its Y center, as we indicated before, is 140 plus 30 millimeters. It's minus 170 millimeters in this case. The hole will show up as a negatively weighted mass. We'll write it as minus 3 times 10 to the minus 5th kilogram per millimeter squared, and has a radius of 15 millimeters, so this is times pi, 15 millimeters squared, and that number turns out to be minus 0.0212 kilograms. So the location H for the center of gravity should be, it's actually shown in the figure as though it's less than half the length of the rod, but actually with this larger mass at the end of the rod, we expect it to be biased in the other direction. We expect H to be greater than half the length, greater than 70 millimeters. And so we'll write H equals the center of gravity equals the mass weighted average of these different centers, and I forgot to make a note that the center of the hole is going to be the same as the center of the plate. If we plug these numbers in, we end up with H being equal to minus 113.7 millimeters. Now we can look up in the back of the book the mass moments for axes that go through the center of these planar or linear objects. If we do that, we find the following. For a thin rod, the mass moment about an axis through the center of gravity perpendicular to the long axis of the rod is 1/12 its mass times its length squared. If we look up the result for a similar axis through the center of a rectangular plate and then let the two sides of the rectangle become equal, for a square plate we have that the corresponding mass center will be 1/6 ma squared, where a is the edge length of the square plate, so in this case a would be 60 millimeters. And if we look up the mass moment through a center of a circular plate, we actually have already seen this, whether we call it a circular plate or a disc or a cylinder. Through its center, we know that this is 1/2 mr squared. So we'll use those results as the basis for our calculation. And what we'll have here for the mass moment through the center of gravity of the whole pendulum is the contribution first through the center of mass of the straight rod, so that will be the mass, that will be 1/12 the mass of the rod times its length squared, and then the parallel axis offset is its mass times the distance between the center of mass of the pendulum and the center of the mass of the rod squared. So this will be 113.7 minus 70 millimeters squared. For the square plate, we have 1/6 its mass, which was 0.108 kilograms, times its edge length, 60 millimeters squared. And the parallel axis offset again is 0.108 kilograms times the distance between axes, 170 minus 113.7 millimeters squared. And finally, for the circular hole, our mass is negative, so we'll put a negative out here. We have 1/2 mr squared and the parallel axis offset is again this value. We add all those values together and we get, for the mass moment about the center of gravity of the pendulum, is 734.4 kilogram millimeters squared. Now we can generate the mass moment about any other parallel axis directly from this. We could write the mass moment of this pendulum about A is the mass moment of the pendulum about g plus the total mass of all the constituents times d squared, where d is, in this case, d will simply be the y-coordinate because the position of A is 0. So if we take our value of 734.4 and add and find for the total mass 0.1988 kilograms, and the distance is 113.7 millimeters squared, and that gives us a value of the mass moment about axis A of 3303 kilogram millimeters squared. The radius of gyration about A then is just the square root of IA over the mass. So the square root of 3303 kilogram millimeters squared over 0.1988 kilograms, and that radius of gyration turns out to be 128.9 millimeters. For our last example, example 5, we have a circular cylinder that has a conical hole in it, has uniform density, and we want to use composite shapes to determine the mass moments of inertia about the x and y axes. We can express our answer in terms of density, mass density, and the dimensions r and l. We could also, after the fact, repeat this problem using integration to verify that we get the same results either way. So we'll do both of those. We have here a summary of the information we get from the inside back cover of the textbook. One of the things to be aware of is that the local x, y, and z axes that are embedded in objects in the back of the book may not correspond to the x, y, and z axes in the problem statement. So we'll notice here that if we want to find the mass moment about the x-axis in our problem statement, we want to be sure to use the values for IZ for the cone and the cylinder, because that corresponds to the axis of revolution in both cases. Also, we want to be aware of where the center of gravity is for using the parallel axis theorem. So for instance, for the cone, in the inside back cover of the book, the center of mass of the cone is shown as 1/4 of its height measured from the base. In the present case, when we go to find mass moments about the x and y axes, we want to keep in mind that the distance from the center of mass of the cone to the origin of our problem coordinate system is actually L minus L over 4, or 3L over 4. So of these two calculations, Ix is the easier one, because again, the x-axis of the problem statement coincides with the x-axis of the centers of mass of both the cylinder and the cone, so there's no parallel axis offset. So for the cylinder, the value that we have corresponds to IZG on the inside back cover of the book, so it's 1/2 mr squared. So we have 1/2 times the mass of the cylinder, which will be mass density, times the volume of the cylinder, which will be rho times pi r squared, but its radius is actually 2r, times its length. There's our mass. Then multiplied by its radius squared, which is another 2r quantity squared. And then we're subtracting from that the corresponding mass moment of the cone, which we're treating as a negative mass. And that value, again, the value that we're looking for is IZG, so 3/10 mr squared. So we'll have minus 3/10, and the mass is mass density times the volume of a cone, which is 1/3 pi r squared h, and the radius of the base is just r. So we have 1/3 pi r squared times L, and then we have another r squared. So we have a bunch of common terms we can pull out here. We'll pull out a pi and a mass density and an r to the fourth and an L. And then what we're left with for the cylinder is 1/2 times 2 squared times another 2 squared. And for the cone, we're left with 3/10 times 1/3, or minus 1/10. And so what we get here in parentheses is 8 minus 10, which is 80 minus 1 over 10, which is 79 over 10, rho pi r to the fourth L. Now for IY, this is going to be more complicated because we will have a parallel axis offset. The local y-axes through the centers of mass of the cylinder and the cone are offset from the y-axis of interest. In this case, we can use the values of IYG in both the cone and the cylinder cases because that does correspond to an axis that's perpendicular to the axis of revolution of those objects. So we'll have for the cylinder first, we have 1/12 the mass times 3r squared plus h squared. And then the parallel axis offset, we have an md squared and the distance between the two sets of y-axes is just half the length of the cylinder. Now we have to subtract off from this the contribution of the cone, which is 3 over 80 times the mass of the cone times 4r squared plus h squared, and the parallel axis offset is the mass times the distance between axes. And here we're using L minus L over 4, or 3/4 L squared. Now again, we can pull some things out here to make this a little simpler. We're going to have a common rho pi r squared L. And if we look at what we have left, for the first term we'll have a 1/12 times 2 squared times, we have 3 times quantity 2r squared, so this is going to be 12r squared plus L squared. And then we have from the parallel axis term another 2 squared times L over 2 squared. And we're subtracting our contribution from the cone. We'll end up with a 1 over 80 times 4r squared plus L squared plus 1/3 times the 3/4 L squared, which is going to be 9/16 L squared. Multiplying these things out, we get from our first term a 4r squared plus 1/3 L squared, and then our parallel axis offset gives us another L squared, and we're subtracting. Our first term is a 1/20 r squared, and then we have a 1/80 L squared and a 3/16 L squared. This is a 1/5 L squared. So our IY we have an R of 4R squared minus a 1/20th R squared, which is a 79 over 20 R squared. And then we have a 4/3 minus 1/5 L squared, which gives us a 17 over 15 L squared. Now these expressions are not the most natural expressions, so it would be valuable if we could verify these in a different way, and we can do that by going back to our integration approach and constructing alternative expressions for these mass moments based on, in this case it'll be an annular disk element, where the outer radius of the disk is fixed at 2r, and the inner radius of the annular disk scales linearly with x, and we can see just from the straight line that describes that inner radius that it's simply rise over run times x, so it's r times x over L. We also emphasize again that we're going to be summing these disk elements over the x-axis, and we will write our expressions for an increment of mass moment based on local axes that go through the center of the differential element, and we will relate those back to the x, y, and z axes of the problem coordinate system. So our increment of mass moment about the x-axis is the same as the increment of mass moment about the center of mass axes for the disk element. And here this only varies from what we had before. This was a pi over 2r to the fourth, but now we have an inner radius as well as an outer radius, and this is going to look like our fixed or constant outer radius to the fourth minus the inner radius to the fourth. There's our area moment rho dx. So our value for Ix will be the integral from 0 to L pi over 2 16 r to the fourth minus r to the fourth x to the fourth over L to the fourth rho dx. We can pull a bunch of things out of there, the density, the pi over 2, the r to the fourth. We have the integral from 0 to L of 16 minus x to the fourth over L to the fourth dx, which integrates to 16x minus 1/5 x to the fifth over L to the fourth, evaluated between these limits. And we find that 16 minus a fifth is 79 over 5, so this again becomes 79 over 10 rho pi r to the fourth L. That's exactly the same expression we got using our composite approach. To construct an increment of mass moment about the y-axis, that will be the increment of mass moment about the center of mass of the differential element plus the parallel axis offset, which will be x squared times the increment of mass dm. And again, because this is a disk element, I know that the mass moment about the local y prime axis will be 1/2 the mass moment about the polar axis or the x prime axis, and again that's a consequence of the relationship between the area moments. So this is going to look like pi over 4 quantity 2r to the fourth minus r x over L to the fourth rho dx plus x squared times the cross-sectional area of the disk, which is rho times pi, times the outer radius squared minus the inner radius squared times dx. Now I already know what this is going to integrate to. This is just half the first term. This is just half the term we got for ix. The only difference here is we have a pi over 4 out in front instead of a pi over 2. So I'm just going to say that this term, this first term, this integrates to half the value we calculated in the first step. So that's just going to be 79 over 20 rho pi r to the 4th L. And that leaves us focusing on this second term. Integrating that term we have this expression which integrates to this. Putting that all together then, we again get that Iy is rho pi r squared L, 79 over 20 r squared plus 17 over 15 L squared. So again, this is exactly the same result we had using our composite approach. So in closing, we have a couple of different methods we can use for evaluating mass moments. We can use an integration approach. We can use a composites approach. It may occur to you that there might be shapes which don't lend themselves to either approach. That is, we can't really represent the object in terms of simple shapes or named functions. It turns out that there are also a set of very simple experiments that can be constructed that allow us to infer mass moments of inertia by observing other quantities. And so one of those three approaches, either computational, analytical, or experimental, allows us to get the mass moments of inertia which we need for our rotational dynamics equations.